All right, hello everybody. This is Tyler with ARIMA Security Research. So today what we're going to do is go through one of the articles that I wrote on Medium and had published in Tor Data Science called Predicting House Prices with R. And we're going to use ARIMA models and the Case-Shiller Index and a little bit of R to figure this out. So what we're going to do is predict the next year of U.S. housing prices. We're going to get experience using some real economic data, going to visualize it, understand some assumptions about the data, and learn predictive modeling using the ARIMA method. So let's jump into it. So, when you get the data, I would take a look either at the ARIMA website and go to the post in there and get the link to the GitHub, or in the Medium article you can have a link to the GitHub, but we should go to a place like this. The article was written for this data. If you have newer versions of that, okay. But we're going to take a look at it from this perspective, and we're going to go ahead and use this one. And let's get into it. So the first thing that we're going to want to do is open up RStudio, and in here we're going to see everything just as we are, but we want to click on the white page up here and the green circle and do R markdown file. I'm going to call this Case-Shiller test because I've already done this before, but we're going to go ahead and put that in there. When you get a new R markdown file, a lot of this junk, you just don't need it. It's just in the way of demo stuff from the R people. I usually like to give myself a few lines at the beginning, and we need to import our libraries first. So let's go over here to the big C, the big green C with the plus sign, and add a chunk of R. We'll go ahead and paste that in and modify that just a little bit. So if you run this and you get forecast, tseries, and tidyverse to come up, great. We're in a good place. If for some reason you're getting an error, say package isn't installed, you can also do the install.packages name of package. So you could, like, if you didn't have forecast, you could do install.packages forecast, and that would work just fine. And you'd be able to install that and then go ahead and just get rid of it when you're done. You only want to install packages in R exactly one time. You don't want to keep installing them, right, over and over and over again. It's a good way to make R angry, and we don't like making R angry. So one of the notes that I'd have for you here is if you're a Mac user, be careful. Windows and Linux doesn't seem to affect this, but when you go and download the data from my GitHub or from Fred or wherever, you're going to get a file as a CSV file. And that CSV file, you want to save that and put it in a folder that you're going to work out of, right? So in my case, it's called Predicting Housing Prices, and I just put the data in there. If you download it on a Mac or Windows machine, don't worry about this, but if you have a Mac, do not open that file in numbers. So if you download a CSV, open it in the numbers application that comes with Mac OS and just close it. There's a real good chance that the way that that data gets, or that file gets read and moved around in terms of encoding is going to make R mad, and it comes up as really strange characters. So just if you're a Mac person and you accidentally opened it and opened with numbers, just delete it now, download another copy, and don't open it with numbers. It's fine if it opens with Excel, but not with numbers. So what we have to do next is make a working directory. So we're going to set our working directory. There's a complicated way to do it, and there's an easy way to do it. If you go over here to R and in the bottom right quadrant where there's files, plots, packages, all this stuff, if you're in the Files tab, all the way over here on the right, there is 3 little dots. You can click on that, navigate through your directories on whatever operating system you're in, and then you'll be able to find the folder that you're going to work out of. Once you found it, go ahead and click on More and click on Set as Working Directory. So that's going to shoot a little bit of code down here to your console, and we're going to go ahead and paste that in there and set my working directory to this whole thing. Do you have to do that? No, but it makes it a little bit easier working with data and saving files and that kind of thing. So we're going to open up a chunk of data and actually, or a chunk of R and actually import our data. So the data that we're going to import again is the Case-Shiller Index about housing prices. I have it loaded up right here, and we've got the first few rows of it to print out. So if we got that far, we're in pretty good shape. Next thing that we need to do is understand that the ARIMA model that we're going to pass this into, the data has to be structured as a time series. So we'll get into ARIMA models a little bit more, but the important thing is we have to get this data into a time series format that will pass into the ARIMA model. So let's go ahead, copy the next chunk in, and we'll go ahead and paste that. We'll break these out just a little bit so they're a little easier to read. And here we go. So what we want to do is shorten up the name of one of these columns. I don't know about you, but I don't want to remember how to type this a whole bunch of times. So I'm going to change the names of the Case-Shiller object in the second column to units. So if we open up the Case-Shiller as it is now, it has date and SPC, blah, 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 right? So I don't really want to type that. So what we're going to do is change that to units. It's going to be a lot easier to deal with. The next thing that we want to do is create an object called CS units that takes our Case-Shiller data and the units column and just makes that into a separate object. Can you do this all in one step? Sure. I like doing it this way because it's a habit to be in where people, myself included, tend to not be able to write the code they actually want the first time. So sometimes you goof up objects. You don't have to rerun a whole bunch of code to fix data that you goofed up when you could have just made a separate object, especially if they're small. So I like doing that, and then I'm going to create my time series object. So we're going to use the TS function, and into that we're going to take the CS units. We're going to start it in the year 2000 in the month 1, January, and we're going to have a frequency of 12. So what that's going to do is it's going to take our data of our units, which happens to be in monthly data on January 1st, and we're going to create the object Case-Shiller for the time series. And give it a second, and here we go. We've got all of our data in a time series format from January of 2000 up through July of 2020. So far so good. We've got the whole chart. When we get into ARIMA models, there's a few things that we got to keep straight. So what I'm going to do here is walk through a little bit of how you figure this out. I've spent a lot of time trying to find a better way to do ARIMA models, manually going through all the values and everything. The automatic function works the best, and it always gives you the right answer. I've never had it give me an answer that was worse than doing it manually. So when you have ARIMA, it has 3 parts. It has the P value, the D value, and the Q value. So ARIMA means auto-regressive, integrated, moving average. The P value deals with the auto-regressive part, making linear regressions. The integrated part deals with the D value, kind of the number of lags. The number of times of differencing is how it's defined. And the Q value, which is the moving average part. So when you combine linear models with the moving average and integrate them with time lags, you generate ARIMA models. Right, so we're going to do that. We're not really going to do it by hand. If you want to, you can just use the ARIMA function and then pass in P, D, and Q. Do whatever you got to do on that end, but if you can just use the automatic one, I would use the automatic one. It usually does it right. So, give it a second. But all we have to do is do auto.arima and the name of our time series data set. So we've got some auto-regressive stuff, and we've got some moving average stuff. All right, so it calculates a whole bunch of numbers and gives us an AIC and a BIC value. All right, so it's these are just going to give us the coefficients that are used to form the models, and really all we have to do here is take it that we've made the model, and there is a little bit of trust and magic involved, but it usually does the best. So let's go ahead and check our accuracy. Again, like these things are not supposed to be super accurate, but let's go ahead and check it. We've got all kinds of different measures, whichever ones you want, and we'll see how actually accurate it is. Now, if we go ahead and plot this, the next chunk down, we're going to plot it and make a forecast. So what's cool about this is you can embed the forecast function inside of plot. So we're going to forecast with our fit model that we just made 12 months in advance. 12 units will be 12 months. We'll have our X label be the date, Y label be units, and we'll title the thing, and we'll just make a basic plot. All right, so we see that the data goes up and down, up and down, up and down, up and down, and our predictions are the blue line. The dark gray line is 80% confidence, and the light gray lines around it, or kind of the bands, is the 95% confidence. So you'd read it as the blue line is the forecast, dark gray is we're 80% sure that the real value is going to be somewhere in that range, and the light gray, it includes our forecast and the 80%. So you're 95% sure that somewhere in the light gray area is going to be the real value, right? So, and we're only going off one column of data. ARIMA models are not by their nature the world's most accurate thing, but they are, helpful sometimes. So it's great to have it in a plot, but sometimes you want your data in a table. So we'll go ahead and make a little table called pred values, and we're going to do the forecast with our fit model and go 12 months in advance. This is exactly what we did, just kind of broken out so we can really see it. What is our forecast? What's our low and our high 80%? What's our low and our high 95%? So, this is the blue line, the 80% are the dark gray part, and the 95% are the light gray part of our graph. All right, so those are the numbers that they correspond to. And, now that we've just showed how to make the model, one of the things that you might want to do sooner rather than later is figure out whether your data is autocorrelated and figure out whether it's normal. So one of the things that is done a lot is qqplots and the Box.test. So if we run a qqplot, ideally what you want to see is a straight line with pretty much all your data on the straight line. Down here where we're kind of looking at the bottom left corner, things start to drift away. Up here, there's one that may or may not be an outlier, but the further away your values are from that straight line, the more likely they are to actually be an outlier. Things look pretty normal. And if we look at our Box.test, what we're trying to figure out here is our autocorrelation idea. We're trying to figure out whether it's autocorrelated. Autocorrelation is bad. No autocorrelation is good. So we have a p-value of 0.82. And how we read that is it's a big p-value, which means that our autocorrelation is not significantly different than 0. Right? If we had a p-value of 0.05 or smaller, we would say, we're 95% sure that our result is not due to random chance, that our autocorrelation is different than 0. That'd be if we had a small p-value, and then you could say, hey, we've got autocorrelation, and then you have a whole other set of problems. So, as far as this, we're in good shape. There's no autocorrelation, and we're able to get things, figured out. So one of the things that you may have noticed is that this data looks really, really, really seasonal, right? What it really means is, kind of suspecting that housing prices go up in the summer and down in the winter, right? So let's explore that a little bit. And we're going to do something called a seasonal decomposition. But what we're going to do first is go down here, make a new chunk, and we're going to create a new object, and we're going to log transform our time series data. So our time series that's here, instead of using the real values, which are in the hundreds of thousands, we're going to log transform it and squish it down. have pretty small numbers. So let's go ahead and run that and see, make sure that it worked. That looks like we were log transformed. Now what we're going to do is we're going to fit kind of a seasonal decomposition function in here. So let's go ahead, break this down. We're going to fit to, and into that STL is the seasonal decomposition function. We're going to pass the log transformed time series data into, and this swindow.period helps it run. It's just more of a formatting thing for the function. And then we're going to plot it. We're going to plot our seasonal decomposition and give it a title. All right, so we're looking at this. There's our raw data. Our seasonal is it is definitely seasonal. And what's cool is you can extract the trend. So we kind of have this somewhat of a super cycle within the real estate markets. And you can use those, and this whole remainder idea is looking at the trend versus our data, and when we have that, you can kind of figure out how much it's going to vary a year. So, with this, you can look at it and say this is definitely seasonal data. And last thing that we're going to do here, at least with plotting, is create what's called a season plot. So if you had any doubt before, and you have seasonal data by month, what we're going to do is plot that data, and we're going to have our year labels on, and our color we're going to leave to rainbow 20. We're dealing with 20 years of it basically. You can have less colors, you can have more colors, you can make them all the same, whatever. Rainbow just chooses a different color. And the number is how many different colors it'll choose. So you can have a season plot that looks like this, and you can definitely tell that housing prices are low in the winter, and they rise into the summer. So you can do with that what you want, but when you plot out all the data, it definitely comes out looking like that. So we have everything looks seasonal, and if you want to do kind of for bonus points, if you want to do ARIMA models based on your log transform data, we do basically the same thing we did before, where you have the auto.arima function where you just pass in your log transform data. That'll make another fit. So your AIC and BIC values went down quite a bit, and our log likelihood changed. So it's going to be the same idea, and you can check the accuracy with this little thing, kind of the next chunk down. You can have your accuracy of your model actually fit into a data frame. So we can do that for our original model, and we can do that for our log transformed ARIMA model, and then you can bind them together with rbind. So bind the rows with the original fit accuracy over the second fit accuracy. We'll bind them on top of each other, and we can take a look at their coefficients of errors. So in this case, I'm prone to root mean square error. We in our first one, we had a pretty high error rate, and down here we had a smaller error rate. Now a lot of that's due to the log transform, but we do have a smaller error, which is probably good. So we'll probably have a log transform it. So let's see what happens if we plot that. Right, so we're going to do the same thing we did, but we're going to forecast using our log transform model rather than our original one. And the plot's going to look pretty similar. All right, over here the units are smaller, but we're still forecasting things about the same. And right now we're going to take a look at how different the models really actually are. So if we go ahead and paste in this code, we'll break down, we'll break these down here, and that looks to be probably okay. All right, so let's go ahead and run this, and then we'll take a look. What happened, we created our original pred values. I just brought it back. So we have our prediction, and then we also have our other predictions. put these together from the new model, and then what we're going to do is to get out of a log transform, use the exp function. So you do exp out of our new values, and that'll get you the real values. So I'm going to create this thing called merged df, which is going to be a data frame. We're going to have a date column, and if you really want to make it a little easier to read, you can do shift enter to break these things after the commas. Makes things a little easier to get a hold of. So we have a date column, we have an original data forecast, we have the log transform data forecast and the real numbers, and then what the difference is. So at the beginning we're pretty close, and as we get further away, the differences in predictions get bigger and bigger. So that's kind of also a function of the ARIMA model, is a few months in advance you can be a little more accurate than you can a year in advance, which kind of makes sense with housing data. You never know what's going to happen. But as far as getting it out of here, creating an ARIMA model, getting it to fit, finding an easy fit, transforming your data, finding out what the differences are, whether you should log transform or not, is it normal? All those things we went through, and as far as any other questions, make sure you reach out in the contact form or in any of the comments in the videos. You can always reach out to us, and we can keep mashing those buttons together. So again, this has been Tyler with ARIMA Security Research, and look forward to seeing you in a new video and on the email list, and like and subscribe.